Okay, YouTube, in this last video we're going to be discussing compounding interest, which is something that we're often interested in doing. And so, since we are so interested in this, we are going to need to make ourselves familiar with what we call the natural base e. Okay, and so when we talk about the natural base, we often represent exponential functions as having some base e. And what I can tell you is that this e is actually a number. It is called Euler's number. It's named after a Swiss gentleman, Leonard Euler, and his last name started with an E, so we give it, give him credit. We call it E. So this number E approximately is about 2.718281828, 159 or something like that. But what we can get away with is about 2.718 is a good approximation of this. This is a number that we're going to be using in this video, and it is worthy to note that it is an irrational number and cannot be listed as a repeating decimal. We can't write it all out, so we'll just use the base E. So in terms of compounding interest, the primary difference between our two methods are going to be, are we compounding it n times per year, or are we compounding it every moment of every day continuously? So we'll start with the n times per year, and so you'll often hear things like quarterly. And when we talk about quarterly, what would that mean in terms of n times a year? We would say that this is like 4 times a year. And if we had something where it's biannually, I can't write that there, biannually. I believe that biannually is once every 2 years, so we'd say like that's like half a time per year. But what I want everybody to get used to is the fact that we're saying that n is the number of times this happens per year, and that's part of our formula. So we have A equals P times the quantity 1 plus r over n to the nt. So we're going to run through what each of these values is standing for, but we say that A really is this amount that we have right here. And we could say that this is just a function of time over here, but we use the capital letter A. So the amount of money, say, we have in an account is equal to the principal, which our principal really is the starting amount in our, say, account in this particular instance. So principal amount is the beginning amount. We say n is the number of compounds per year. So again, if we said quarterly, n would be equal to 4, but if we said biannually, we would say n equals a half. So our rate, you'll notice that I scribbled here that it needs to be written as a decimal. It's going to be given to you likely as a percentage, but not always. It doesn't have to be. And then last but not least, we're going to say time, and most traditionally we're going to say time is measured in years, but time could be any unit that we choose, I suppose. So for our n compoundings a year, we're going to use this first formula. For the continuous compoundings per year, this is actually my favorite formula and the one that I prefer, but you'll notice that there are some similarities between this and the last example where we had only n times per year. So we have the amount is this A over here, and P is still our principal amount, or what we're starting with. Instead of a base of 1 plus r over n, we have a base of just E, and it's to the RT and not to the NT. So we will need to know the principal rate and time in order to give you an amount at that given time. So that being said, what I want to do is this. We say that a total of $12,000 is invested at an annual interest rate of 9%. What I want to do is find the balance after 5 years, compounded two ways, once quarterly and then the other one continuously. So I think that the important thing here is that we start off by writing down what we know we have. So we have A, P, rate, time, and the number of compoundings per year if applicable. So because this first one here says quarterly, that is n times per year where n is equal to 4. So we are going to be using our first formula that says, well, the amount's equal to what you started with times, in this case, the base is 1 plus r over n to the nt exponent. So that being said, we have a total principal amount or a starting amount of 12,000. Don't use a comma here, you'll just confuse yourselves. We say, okay, it has an annual interest rate of 9%. So I'll write 9%, but right next to this, what I want to write is 0.09. Remember that you can take a percentage and rewrite it as a decimal by moving that decimal twice to the left. So we get 0.09 as 9% as a decimal. We say find the balance after 5 years. So we have a time here, 5 years. And in this particular case, for our first example, our n is 4. What we're really asked to being asked to solve for is this value here. Let me switch back my pen size here. This value of the amount. Try again. There we go. So we're looking for this amount value right here. So let's plug in what we know and we'll go find what we don't know. We say the amount then would be equal to the initial 12,000 times 1 plus now our rate must be expressed as 0.09, and this is over the time, in this particular case 5, and this is to the n times t, so two numbers up here. We have our n, which is 4, and then our t, which is time, here is 5. So I'm going to simplify this a bit, and I'm just going to use my calculator to evaluate it, to be honest with everybody. So we have 0.09 over 5, and then this is all to the 20 power. So using our calculators, parentheses really going to be our friends here, but let's go ahead and start with our initial 12,000. I say 12,000. We're going to put all of this stuff in parentheses, so I say 1 plus. Now, I'm going to put a subset of parentheses in here where I'm going to say this is where I'll put my 0.09 divided by 5 inside of that. And then I'm going to take that and I'm going to put that all inside with this 1 plus that amount. And we're taking this all to the 20, excuse me, 20th power. So I'm going to hit enter here, and it looks like after 5 years, if we had a 9% interest rate and we started with $12,000 and it compounded quarterly, after 9 years we would have another $5,144-ish on top of what we started with. So we say this amount is, I'm going to write it this way, approximately 17,144 point, and I do want to get this decimal here, about 97, so about 97, and we need to label this with what we have, which in this case is dollars. So now how would this differ if we compounded continuously? And one thing that I want to kind of confront is this. When we say continuously, I really literally mean every moment of every day. It compounds infinitely many times. So what we're looking at here in this situation is a situation where we still have the same principal amount. We still have the rate of growth. We still have the time in years. We just don't have an end value because it's always continuously compounding. So we have A is equal to our 12,000, or our starting number, times E, our 2.718-ish, to the power of 0.09, times, in this case, in particular, 5. So we have A equals, now, using our calculator, the first thing we want to find is our E to the power of button. So I'm going to clear all this out. If you find your ln button, this is our natural log button, chances are that e to the power of x is right behind it. So for instance, if I hit that e to the power of button, I just say e to the power of 1, you can see that of course e to the power of 1 is itself, and we get this 2.718 number. What we're going to need to do is use that button in this case. We say to do 12,000 times now e to the power of, and in this case we have 0.09 times 5 up in our exponent, and I'll end that parenthesis and hit enter. In this case we have 18,819.75, 18,819, about 0.75, and this is an approximate, and this is in dollars. So this would be our continuously compounding interest, and you notice that there's substantially more because it compounds more times a year than 4. So that's how we calculate compounding interest. Know the difference between continuous and n times per year, and know your number E. Cheers.